All right, so now it's time for some code. So let's see here. All right, so I actually just took this straight up from SciPy. So one thing I'm going to say is that I don't like OLS as compared to SciPy. I'm just more familiar with SciPy. I have bad memories of LS, I think. So that's kind of why I try to avoid it. But know that you can also do this either way. We're going to use basically the ANOVA test, which SciPy stats doesn't call it ANOVA. It's called the F1 way. F1 way, basically the F test, which is the ANOVA, and one way meaning doing one tail, right? And note that the F test, the F distribution looks something like actually, why am I drawing it? You know who's better at drawing? Everyone else. So there you go. This is what the F distribution kind of looks like. And it just depends on the number of degrees of freedom, essentially. So you can kind of see there's the red one and different spikes and stuff like this. So anyway. Okay, so we're going to use this guy right here. And basically, we're just going to feed in the samples. And then it'll return our statistic, our F value, right, our F statistic. And then what's nice is that SciPy just says, hey, here's the p-value automatically calculated, so we don't have to convert it over to the right F distribution. I took the data straight up from here, so we're going to play around with it. So I'm going to go ahead and import these guys just for us to basically, all I really need is this guy to do the F1 way ANOVA test, right? But I'm using this other stuff so we can kind of play around with it. And so I just took this data straight up from the website, so just kind of basically just to have something. And I think it's something to do with like different muscle shells and stuff like this. And these are the different like lengths and widths of like the shell or something like that. I don't really care, I just data. So I'm just organizing in a nice pretty way. And you can see here, I get my nice data frame, which basically is like where these shells were from, and then basically the shell. And I note that it's standardized too. So these are not the literal measurements, but it doesn't really matter. We just standardized it to a certain value. Okay, everyone follow me so far? Okay, so I got the data. Just to kind of look about like what this looks like, the distribution data. So I just made this quick box plot, right? Basically the area, right? So basically the area meaning like where these shells are found, right? So these are all the different groups. And then I also made a swarm plot. So these are the box plots, right? And then the y-axis is the shell standardized error. So like normally if I got rid of this guy, this is what you guys normally used to seeing, this part. But swarm plots from Seaborn are super useful because they actually show you where the actual data points are. So this can be really nice for a small amount of data or even just big amount of data, because you can also change the alpha. So if there's a large amount of data, we can actually set this up to like 0.4 and you can see it's a little bit lighter. So if you have many, many data points that are all on top of each other, changing the alpha basically allows you to kind of see where they're clustered around versus just being like a big mass of something. But since there's not that many, I'm just keeping it about near 1. Okay, so you can see here already is that this seems to be clustered around really closely, but you can see there's a couple outliers right here. See that? Okay. So now what we want to do is like, okay, let's go. Oh, I also made a little subplot. So the same idea here, but I'm using a violin plot. You guys have seen violin plots before, right? Yeah. So this is a violin plot. One nice thing you can do is basically this BW.3. So BW, I can't remember what this stands for, but I think it's something like something width. But basically this says like how much what's it called? How much the violin plot should basically form around each data point. So if I get rid of this, you'll see that this is the normal default violin plot. And then if I add this guy right here, what's happening is forming closer around to make it really emphasis on where the data points are. I kind of like this a little bit better because then you can see a little bit like how squeezed off like this part is right here. And if I go ahead and just comment that out, you can see it's not as obvious. It seems like there's a lot of data points in here. Okay, cool. So this is just me visualizing the data, seeing how it looks. All right, sound pretty good? All right, then just to do the F1 way test, I just feed in each group's data. So remember each of this, these points right here are just literally the measurements. So it's kind of nice because that's like, you don't really have to worry about like how you get this data. You're just like, oh, just feed in a NumPy array of this data. So this could also be in a series. And I get this, the F statistic, which to be honest, I'm gonna ignore all the time, pretty much every time. All I really care about is the p-value, and see the p-value is less than 0.05, very small. So there is a significant difference. Now, one issue with this though, is that you, from the p-value for the F1 way ANOVA tests, you don't get to know why it was the value it was. Like, it's just like, oh, there was a significant difference, but it doesn't tell you which one of these are more significant than the other ones. Okay, so the only real way to do this is essentially take multiple t-tests, compare each one of them. But at least if you see there's a p-value that is very small, it means that there is a difference amongst this group, and you have to just find that difference. So at that point, you might actually like visually look at it and say, okay, which ones actually look reasonably different from the rest of the group, and determine from there, and then maybe do multiple t-tests, or you do a t-test on all of them, which is entirely possible. But also if you have 50 different groups, you basically do group 1 versus group 2, group 1 versus group 3, group 1 versus group 4. It's a lot of tests right there. Now computers can do it pretty quickly nowadays, but it might not be the point of what you're trying to do. You might want to instead say, okay, let me look at these specifically and then investigate these further. Okay.